Alright, thank you and congratulations for clicking the link and moving on to part 2. The Six Sigma Tool Guide, Hypothesis Testing. Let's go ahead and get started. So a little background on the real-life example we'll be walking through. This was part of an overall initiative to decrease cycle time for the loan processing, specifically on the OnlineHypothesis product. The project team had done some time studies and shown that it was faster to process the loans over the phone at the time of the request rather than creating work for another group to do later. So making this one process change decreased the cycle time considerably, but it still left some room for improvement due to the occasional rework that is created when you're due to errors when you're processing loans. So this project was specifically designed to reduce the types of errors that caused rework in the process. So our primary metric here is kind of a pass-fail for each loan approval that goes through the process. So the project team, they implemented several solutions, including a poka-yoke or a mistake-proof template. They assigned very specific ownership of the training and put together some new training materials for the staff. So now it's time to look at those results, look at the old results, look at the new results, and see how much of a difference we made. So step 1, we're determining the expected results. So prior to the process change being made, the monthly results look like this. There were 538 error-free units, so loans that were processed with no rework required, no errors, and 134 that required some amount of rework because of the errors. So this is our expected results. You're going to want to use typically whatever the historical typical results for your process are. This is the numbers that you hoped to improve because of your project. In this case, it was no error 538 and error 134. Those were our two categories. No error and error. Those are the only categories that we'll be using. Once we have made the process changes, then we're going to look and see how many no errors and errors there are. So, step 1 is check, ready to move on to step 2. So step 2 is to get the observed results. And when we use that term, we're talking about the new performance indicators after the process has changed. So once we've changed the process and we're getting new results now, we want to determine if those results are different enough to be considered significant and the result of the change in the process. Because if you see improvement but it doesn't have statistical significance, it's likely to just be by random chance or sort of a fluke, and you want to rule that out. And that's part of that's really the purpose of the null hypothesis. You want to be able to say, no, the null hypothesis is not true. This is not random chance. So we have our observed results. In this case, no error 609, error 63. This is after the new results after the process has changed. And in this analysis, what we're trying to do is determine if those new results are significantly different because of the changes, or if it's just a slight increase that's kind of by random chance. Step 2 is checked. So here we have the observed results and the expected results next to each other. No error 609 and with an error 63. Those are our new observed results. The expected results, what we saw historically, the no errors would be 538 and the error 134. So if the null hypothesis were true, the results before and after the process change should be the same or similar enough to be sort of within statistical arm's reach of each other. Step 3, degrees of freedom. This is super simple. Your degrees of freedom, it's a measure of how much variability is in the process, and it's determined by the number of categories that you're examining. So the equation for determining degrees of freedom is very simple. It's n minus 1, and n is the number of categories that you're analyzing. So in our case, we had two categories. It was errors or non-errors. Just two categories. So our degrees of freedom is 1, because it would be 2 minus 1. If your project has, 3 to 4 categories, if for instance you have a very satisfied, satisfied, unsatisfied, very unsatisfied, like those types of survey results, if you had 4 categories, your degrees of freedom would be 3, because it's going to be 4 minus 1. So number of categories minus 1, that's your degrees of freedom. In our case, we have 1 degree of freedom. So now we're going to compare the expected results to the observed results using chi-square. Now chi-square, it's normally written as kind of x2 or x squared. This is going to be a numerical value, and it measures the difference between the expected and observed values. The equation for it is as follows. It's the sum of the differences between observed and expected values squared and divided by the expected value. It sounds super complicated. It's not as bad when you break it down, and that's what we're going to do next. Here we go. Here is the complicated, intimidating math formula, and I've plugged in the numbers here. So it's not that bad, actually. We observed 609 no errors, but we expected there to be 538 errors. So we take those two numbers here and subtract them. The answer to that we are then going to square, which you'll remember squaring is just multiplying it times itself. We then take that answer and we divide it by the number of expected, which in this case is 538. Then we're going to do the exact same thing on the other side. We observed 63 errors, but we expected 134. So we're going to do that math, and then we're going to square the result and divide it by the number of expected, which is 134. So, back over here on the left, we had 609 no errors. We subtract 538 no errors from the expected number, and we get 71. We now square 71, so 71 times 71 gives you 5,041. Over to the right, on the error side, we observed 63, but we expected 134, so we subtract the difference and we get a negative number. It's negative 71. We still square it though, so we have negative 71 times negative 71, which gives us 5,041, same answer. Remember, when you have two negative numbers, multiplying them by each other, you get a positive. So simplifying that even more, we're saying 5,041 divided by 538 plus 5,041 divided by 134 equals our chi-square, or x2. So we're going to simplify that one more time. 5,041 divided by 538, that's just a way of expressing 9.36. 5,041 divided by 134 is just another way of expressing 37.62. So our chi-square number that we're looking for, x2, is 9.36 plus 37.62. It's 46.98. That is our chi-square number, and we're going to use that number to find out the p-value. So, step 5, significance level. This is the easiest step because it's really already determined. Typically 95% is the significance level that is just sort of the expected standard across the scientific world and the math world. What you're saying when you say when you choose this 95% is that when you are done with your analysis and you are able to either accept or reject that null hypothesis and say, no, I believe that these results are statistically significant, you're going to say that with a 95% confidence level. So we'll get into that a little bit more. As I said, you just want to keep it at 95%. So here we have a chi-square table. If you're doing this formula or this exercise manually, you'll need a table like this. You can get them anywhere online. If you're just plugging in numbers to a statistical calculator, you don't have to go through this process. But manually, you need this table. I want to point out that this DF stands for degrees of freedom. And so this column from 1 to 10 here is related specifically to the degrees of freedom. We had 1 degree of freedom in our experiment. So this row that I've underlined in red is the only row that we are really concerned with based on the 1 degree of freedom. The dark gray area above, you'll notice, these are the p-values. And these percentages represent what the likelihood is that your results are just a fluke. So we want to find our number on this chart. As you'll notice, it starts at 1.32, it goes all the way to 12.12. If I've highlighted 3.84 to highlight the p-value that this represents. If our number came out to 3.84, that chi-square number that we calculated, that would mean that there was a 5% chance, only a 5% chance, that these results were just a fluke. So that implies that they're fairly significant. There's only a 5% chance that this is just some random event happening. It seems like something significant in the process changed. So any number higher than 3.84 in this case only further demonstrates our point. So as you move along, our number of 46.98, that was the chi-square number we arrived at, is literally off the charts. So this is something you can feel really good about and say, I am absolutely certain at probably 99.9999995% chance that the results that we've experienced here based on these numbers are not because of a fluke. Something fundamental changed in the process, and these are definitely statistically sound or significant numbers that we're seeing. So step 7, this is where we either accept or reject the null hypothesis. If our chi-value in this case had been anywhere between 2.71 and 3.84, we would look up into that gray row and see that there was only a 5 to 10% chance, that these results were just random. Because our chi-square was off the charts literally at 46.98, we can say with certainty that these results were not a part of random chance. This was a fundamental change in the process, and so we would, in this case, reject the null hypothesis and accept the alternate hypothesis that yes, we implemented a significant change and have seen significantly positive results. So is there a faster way to accomplish a hypothesis test? Absolutely. There are a ton of online statistical calculators that will help you do this, as long as you're using it from a trusted source. A lot of Six Sigma training sites have them. Most universities, if they have a math department, will have these types of tools online. And usually you're going to be looking for something that says goodness of fit or p-value calculator. One great resource, socialsciencestatistics.com. I've got a couple screenshots on the next couple slides to show you how easy it is to use there. It's a super good resource. Here's a shot from socialsciencestatistics.com. There's their website. As you can see, it's really easy. You enter whatever categories you have, pass, fail, you name it, whatever. Once you've given names to categories, as I've done here, you can plug in numbers, how many you observed, how many you expected. These are the numbers that we used on in our example. I put 0.05 as the significance level. That means I want to be at least 95% sure. Only 5% chance of a fluke. Input your results. Hit calculate. Here is a result. Now it's not going to jump out on the page. If you understand some of the terminology here, you get a better understanding. What I've underlined here, it gives you the chi-value of 46.989, and it says that it is less than 0.0001. So it is less than a 1,000th of a percent chance that this is a fluke. The key words you're looking for is the result is significant at p equals less than 0.05. As long as you see that term, the result is significant at p equals less than 0.05, that's saying that you are 95% confident that you have the ability to reject the null hypothesis and accept the alternate hypothesis that your project was a success. So thank you for checking out the tool guide on hypothesis testing. Anytime you need help, feel free to reach out to the process and innovation team. These types of validations can be tricky, but help is always just a phone call away. We'll be glad to do it. Thank you.